Hey everyone, I hope everyone's having a good time. My name is Kushal Datta and I'm a senior product manager at NVIDIA. And today I'm going to talk about Magnum IO GPUDirect Storage. I think all the speakers in this forum have talked about the exponential growth in data one way or the other. But the point remains, right, where the rate at which we generate and collect data has surpassed trends even after we predicted exponential growth year over year. So latest data shows that we generated around 64 zettabytes in this year, uh, widely surpassing the predicted 58 zettabytes. I wonder what's going to happen next year, but we can all safely assume that it's going to go bigger. So our increasing ability to collect this data faster and more of it using more accurate sensors and large-scale simulations is enabling us to break the boundaries of science and do things we never imagined we could do before. So just imagine how quickly the vaccines for COVID-19 were made. We were indeed moving towards a future where these scientific breakthroughs and marvels will be fueled by the explosive growth in scientific data. And the great success of artificial intelligence impacting every corner of our lives have also been an exciting journey for all of us, right? New models are larger, more accurate, and are helped by this large data to it, and are achieving almost superhuman accuracy. So gone are the days when single box could hold all the computing resource and data of interest to meet these insatiable demands. So as a result, the interesting work now centers around interactions across the physically distributed resources in the data center. And these three, that is latency, throughput, and compatibility, are the most significant factors whenever we talk about large scale data, either storing it or processing it. Latency is not new to this audience here as compute shrinks over generations, especially on high throughput systems like GPUs. We see how IO becomes more important to the overall execution time. The extreme throughput requirements are a side effect of the microservices which are more prevalent in enterprise data centers and cloud infrastructures, right? There are multiple tenancies, there are different types of jobs running at the same time on the same infrastructure, there are different ways that the data is managed and stored and tiered and sharded across these different processing elements. So overall, the unpredictability and the data access patterns is something which demands high throughput and can be significantly improved by acceleration libraries. And third, not the least, is the ecosystem. That means the software stack that needs to be enabled for customers of cloud systems or enterprise customers to be enabled, right? And I took these figures from SNIA.org itself. The storage community is a very large and varied community where there are almost 180 industry leading organizations and more than 2,500 contributing members. So I'm going to talk about the GPU direct storage architecture and how it solves the challenges and brings new opportunities to improve latency, throughput, and enables the ecosystem. The cuFile API, which is the pathway to accelerating your I/O on GPU systems, some micro benchmark numbers and case studies, and call to action. So this is the GPU direct storage from first principles. The left picture shows you how the traditional path is used when any CUDA memcopy or such data transfer into the GPU memory happens always through the system memory. On the other hand, with GPU direct storage, very similar to an RDMA architecture, you can directly copy data from the local or remote storage into the GPU memory bypassing the CPU bounds buffer. Now, what it enables is that by bypassing the CPU bounds buffer, you now can achieve lower latency. You can achieve a much higher throughput. You're not limited by the PCIe to SysMem bandwidth. And of course, you can scale to the you're not bound to the local NVMe capacity. You can scale to the remote storage capacity, and the cuFile APIs give you an API which is very similar to the CUDA programming model, which just is another feather on the cap. I think you all generally understand the flow when you're coming in from the network today, and the only thing that Linux lets you do when you need to provide the address to which you can DMA in in a storage context, of course, must be in the system memory. So you need to make a copy into the system memory and then copy it down to the GPU memory. And like I said in my last slide, the GPUDirect Storage solves that by enabling you to bypass the CPU bounds buffer. And so you reduce the CPU utilization, reduce the end-to-end latency by avoiding the extra copy, and utilize the line rate almost, or provide the throughput almost at the line rate capacity. So note here that GDS is a client library and the client call resides in the GPU. Okay, so let's double click into the GPUDirect Storage software architecture. There is a user space library component to it and the kernel mode component to it. The user library is provided through this file API shared library, and the library provides the application interface to work with the file descriptors and the GPU memory. In Linux, the file system stack works on struct pages and is based on system memory that can be pinned for direct memory access or DMA. Today, this cannot be done with GPU via addresses like I was talking about in the last slide, and block IO driver will return a fault, right? So the way that we handle that is an NVIDIA file system driver, which is a kernel object. So it's the kernel model that interfaces with the file system and NVIDIA driver for managing buffers and IO orchestration and supported kernel-based storage driver. It does three things. First, it provides an alternate system virtual address space and hence struct pages that can be used to act as proxy for GPU virtual addresses. Second, it maintains the mapping between the alternate system virtual address and the GPU virtual address. And three, it provides callbacks to translate from GPU virtual address to bar1 addresses. There's another box in this which talks about the proprietary distributed file system. So if vendors, for example, Veka or IBM Spectrum Scale and DDN Exascale or Lustre, they want to include or integrate GPUDirect Storage in their stack, they will work on the distributed file system, and we can support any other proprietary file system who has a different file system from NVMe over Fabric or network file system. Dynamic routing is another architectural feature of GDS. In the left cartoon, you can see a fictitious system where there are two CPU cores, and each CPU core has a separate PCI switch tree in which there are a NIC and a GPU connected. So there are multiple paths from an NVMe device, for example, connected to CPU socket A to GPU B, for example, right? Either through the inter-socket fabric or through NVLink. Now, the different configurations or the different paths are shown in the bottom table, and all it shows how GPUDirect Storage can find the best route for you dynamically given the source and the target tuple. So if you are using the correct affinitization in this case, which the GPUDirect Storage automatically finds for you, you can hit all the way up to 52 to 54 gigabytes per second shown in the chart on the right using local drives on Gen 4 PCIe. If you use NVLink, then you would do much better than no affinity at all. But the worst case is that no affinitization at all. Compatibility mode is yet another feature. So the point here is that if you have added GDS or the cuFile APIs into your application runs out of the box for all other systems, even though you do not have the required software packages or the NVIDIA file system.kernel object in your system. So the idea here is that the fallback path is the POSIX API. So all the we have tuned a lot of the CPU to GPU paths for our earlier system to see the best performance, and that's what we provide as a fallback path if you do not have the software requirements. So the compatibility mode is just a fallback path in case you don't have the necessary ingredients to run GPUDirect Storage with the highest performance and throughput configurations. Having said that, the chart at the right shows that there are certain IO sizes where compatibility mode can show a little bit of degradation, but again, it's less than 5%, so we are comfortable with it. All right, let's talk about the CoFile API. The CoFile API is part of CUDA toolkit, and from 11.4, it is actually integrated with the CUDA toolkit download bits. The features are that the user space file IO library for GDS are DMA and RDMA ready file systems. It supports both aligned and unaligned file IO offsets. It avoids the CUDA mem copy, intermediate copies to page cache and user allocated system memory, all the good things that are part and parcel of the GPUDirect storage acceleration library. There are a few requirements and POSIX guidelines which we have documented in detail in our overview guide. So please visit the link if you need more details. I want to show a sample code written in C++. This code shows you the file write, right? Very similar to other file operations. You open a file and then you get a file descriptor, and then very similar to the operations you do in C sharp. You get a file handle register, and that's what you use for the cofile write and cofile read functions. Once you are done with writing, then you optionally free the developer pointer, free the file register, or deregister the file handle, and then close the file descriptor. So very similar to the file APIs that all of us are familiar with, and there is also parity with the CUDA APIs there. So if you I just wanted to really capture how you would, what are the requirements or necessary steps you need to take if you have an application that you want to integrate GDS with. If it's a C++ CUDA application, you call the CoFile APIs just like in the example I showed you in the before. Install GDS in the system. If it's a DGX operating system, 5.1 version onwards, GDS is available by default. If otherwise, you just install the bits from our web pages. If it's a Python application which uses NumPy reader and you download our NVIDIA DALI Python library, you automatically get GDS because that's integrated with it. Same is the story for Rapids and Spark application provided by NVIDIA. GPUDirect Storage is already integrated in it. So the mechanisms of action for you is nothing different. You just install GDS and get the corresponding libraries, and it should work out of the box. The one thing which I want to provide here, which our engineering team has worked very hard on, is that once you integrate with the CoFile APIs, it doesn't matter whether you're using NFS or NVMe over Fabric or Lustre, for example. Your file operations and functionality should work ubiquitously across all these different scenarios. So that's a great benefit. All right, wanted to share some performance benchmarking. All right, so getting back to the three things that we talked about in the introduction of GDS, the higher bandwidth. These are some very preliminary microbenchmarking we did, and which shows that how GDS shows significant improvement in terms of bandwidth, direct path, leading to this higher throughput, lower latency, and you can see that how the even for larger sizes how there are jitter in the page caches, whereas the latency is pretty stable and smooth with GDS. And of course, since you are bypassing the CPU bounce buffer, you would also get lesser CPU utilization, so more free cores for your applications to scale. Another critical performance point is how GDS performs with local storage. So in a DGX A100 system where there is a 1-to-1 ratio between GPU and NVMe devices that you can connect to through the PCI switch, you can see that how GPUDirect storage for all the important IO sizes performs better and improves overall CPU utilization across the packet sizes. So 3 to 5x CPU utilization advantage and 2.8x performance advantage at 4K. And yep, this is in local drives. Okay, so before we move any further, I wanted to give a rundown of the DGX A100 system architecture because all the rest of the micro benchmarks and the case studies are dependent on this. In a DGX A100 system, there are 8 GPUs. There are 2 CPU sockets. Each one has a PCI switch, and the GPUs are connected to this PCI switches. The NICs, there is a one-to-one ratio from the GPU to the system, network interface cards, and there are 4 of them connected to each of those PCI switches. So this is the reason that if the PCI to or the NIC to RAM or system memory bandwidth is on one PCI lane, whereas each individual NIC has a direct path through the PCI switch to the GPU. So, if you cumulatively, you have a much higher bandwidth between NIC and GPU in the system through the PCI tree. In addition, there are NVLinks which are used for compute GPU to GPU communications, and that is a separate fabric. So this is the compute fabric, and the NICs connected to the PCI switches. In addition, so these are called the east-west or the compute NICs. In addition, there are 2 north-south or storage NICs connected directly to the CPU sockets shown on the top of the picture here. So just remember that there are 2 storage NICs north-south, and there are 8 compute NICs east-west. So the standard configuration of GDS on a DGX system is through the storage NICs or the north-south NICs, which are connected to the CPU sockets, right? So in a InfiniBand or an Ethernet 200 gigabit per second fabric, each of the NIC can provide up to 200 gigabit per second connectivity, which accumulatively gives you a 400 gigabits per second or 50 gigabytes per second overall storage bandwidth in that DGX system. And GPUDirect Storage is enabled on this one by default. And the performance benchmark shown in red shows that in the packet sizes that are most prevalent in all the applications that we have seen, GDS on the north-south NICs achieves up to 1.4747 or 1.5x advantage over the CPU GPU path. And more importantly, CPU it also improves up to 3x the CPU utilization. So it's overall a great story. So in addition to the standard GDS configuration using the 2 north-south or the storage NICs, you can also use GDS with the compute fabric or on the 8 NICs that are directly attached to the PCI switches. But having said that, I want to throw a word of caution here because this is not a practical real-world scenario, right? Although you can see how you can scale all the way up to 200 gigabits per second times 8, that is 1.6 terabits per second. It is highly unlikely that any application can actually use such a high bandwidth today. The Marslanders demo that we have created before utilized this fabric, but I think that this is more of a stress test configuration rather than a practical real world scenario. If you have such a use case and you want to use such a high IO bandwidth in your application, please reach out to us. So from an individual DTX box, what we see, to summarize, right, we see 1.5x benefit in read bandwidth, and we see 1/3 CPU utilization or 3x improvement in CPU utilization and near line rate read bandwidth, right? So this is a view that a benefit you get with using GDS on one DGX system. But hey, the real story is that if you are using a super pod configuration or multiple DGX pods, this quickly adds up. And that's what I demonstrate here, right? So with GPUDirect Storage, you are much closer to the line rate and effectively can scale to 96 gigabyte per second, which is using 2 DGX A100 systems compared to only 66 that you can use without GPUDirect Storage. So this is a humongous amount of benefit which GDS brings to the applications that are using on the DGX systems. All right, let's look at some case studies. So the first case study is accelerating one of the deep learning inference use cases, And here we show how GDS, once integrated with the DALI pipeline, benefits the DeepCam model inference on a DGX box. There are two key takeaways from this chart. But before I go there, our baseline is NumPy, optimized NumPy. The middle green bar shows you just DALI without GDS, and then the purple line shows you with GDS. So the first takeaway is that we are almost a order of magnitude better than the baseline, right? 6.6 or 7x performance speed up in the inference. But another key takeaway is that as you increase the global batch size, your improvement with GDS increases. And this is intuitively, it makes sense, because as you are bringing in more data for your batch inference, you get to see more benefit from the acceleration of the IO pathway. But this is the first time that we are seeing this effect, and it's a very interesting result for us. So we want to see how these results translate into training, and that's the experiments that we are doing currently. And just for reference, DeepCam is one of the MLPerf HPC models, and it is used to identify extreme climate conditions in climate simulation. The second use case is a pure HPC, where we show how seismic simulations are, with good, better, and best compression quality, can benefit from GDS. So there are two different passes, the forward pass and the backward pass in seismic, and in both of these cases, you can see that with best quality, best compression quality, you're getting the GDS brings you the most benefit. And on a forward pass, you get up to 1.3x, and on the backward pass, you get backward modeling, you get almost 1.9x, so 2x benefit. The disk here is the local NVMEs. That's our baseline, and the interesting find here is that this is not a micro benchmark anymore. This is an end-to-end acceleration of the overall application, which is very exciting, and that's more of these results is what you should look out for as we are going to blog about them or show the benefits in them. So our learnings and best practices is what I have shown here. This is just for a quick reference. I'm going to put it out here, not going to do too much of a details, but use this as a guideline as you're tuning your system with GDS. In the first slide, I talked about the three undertones of storage, right? Latency, throughput, and enabling the ecosystem. So this is the chart where we talk about the ecosystem. Our engineering team and the entire GDS team has worked tirelessly to enable a wide ecosystem. And I know that a lot of our partners today are in this call. So we categorize our partners into GA, that means they are all in production, and then in development, that means they are in some stages of, they have already shown expertise in GDS and are some stage of maturity to integrate GDS and making them available to the broader ecosystem. So DDN Exascaler, Vast, Veka, Dell, EMC, they are all file systems, distributed file systems which have GDS included in it. They are already available for your use, so please feel free to visit their web pages and try it out. IBM Spectrum Scale is another very interesting partner for us. So we are coming to market very soon, and I'm very happy with the way the partnership is going. NetApp NFS and BGFS are also two candidates, and we are very excited to take the next steps with them. GPUDirect Storage is the new kid in the block in our GPUDirect family. So GPUDirect is a family of RDMA libraries which enable data movement between GPU and peripheral devices. GPUDirect Storage is specifically focused on storage, but RDMA, GDR or GPUDirect RDMA enables direct DMA path from NIC to GPU memory. And so based on the same idea, and if you can catch the drift, the idea here is to use RDMA everywhere and enable direct path to the GPU memory so that your compute can benefit from the accelerated I/O. Magnum I/O overall is the I/O system of the data center of the NVIDIA data center. NVIDIA has invested over the years in a lot of the IO libraries, including GPU to GPU communication and GPU to storage. We talked about GPUDirect Storage, but that is one of the elements of the Magnum IO toolchain, in which there are the four pillars: the network IO, which includes traditional GPU to GPU comms libraries like Nickel and NVSHMEM and CUDA-aware MPI, things like that. In the storage bucket, any acceleration libraries is GPUDirect Storage and Snap. In inline compute, we have the in-network computing libraries like Sharp, which is a hierarchical aggregation protocol running on the switch, aggregates the gradient synchronization or gradients in the switch instead of the GPU SMs. Tag matching, and then other libraries coming on this bucket. And of course, the last but not the least is the management of all the data movement. So please look out for all the different technologies coming out for Magnum IO, and see and keep an eye and see how it benefits your application. Thank you again. I think the call for action for all of my listeners today is, please contribute to the Magnum IO GitHub. You can take a look at all the different readers that we are posting there, enabled with GPUDirect Storage. If a certain reader or writer which is interesting for your application use case, please feel free to push it to that. Share it with the community. We will happy to help you on your journey. In addition to that, there are a lot of developer blogs and documentation that we are posting on the GPUDirect family of technologies, specifically focused on GPUDirect Storage as well. And please explore our webpage, where there is a lot more information. This is the great team that we have. I'm just a representative of. I stand on the shoulders of giants, and this is my team. So thank you again for listening to me, and it's been a great pleasure to give this talk at SNIA at SDC 2021. Thank you.